Hi, my name is Dr. John Galaska, and this video is for Research Methods PS 503A at Antioch University in Santa Barbara. And today I wanted to discuss a few things. One is a tiny little bit of vocabulary that might come in handy for you. A couple of words that we discussed in some of our face-to-face classes, and I just thought that these would be good things for you to know. Sometimes when you are unable to get any movement in a client's condition, it's referred to as refractory. So refractory depression is depression that's difficult to treat. And another word that you should be familiar with is iatrogenesis. Iatrogenesis is a severe emotional reaction that can happen anytime you're dealing with a client. These are a couple of words that you might come across in your reading in the mental health field. So they would be good things to have in your vocabulary if you don't already. Refractory, simply meaning difficult to treat, and iatrogenesis, meaning a severe emotional reaction. That can happen at any time when you're working with people. I would like to talk a little bit about the labeling of quantitative research. There is experimental research, and then we have quasi-experimental, and we have non-experimental research. You know the requirements for experimental research. It's fueled by curiosity. Upon making some observations, you may have some conjectures about relationships among variables and the things that you have observed. And so you make a hypothesis. You fine-tune that hypothesis so that it is testable. You gather some results from your testing. You examine the data, and then you make a conclusion as to whether you accept or reject your hypothesis. And often you just start over again. We're going to be talking about hypothesis testing in just a little bit. But right now, this is the experimental side of quantitative research design. And you know that the research article that you are critiquing needs to be an experiment. I trust that you are getting some facility with utilizing the databases that are available through the university library system, and you know that our librarian is waiting in the wings to help anybody who is having difficulty with doing database research. On the other side, we have non-experimental design. One is referred to as quasi-experimental and another non-experimental. There is no defined line between these two. It's rather fuzzy. And this fuzzy line, this demarcation, is determined by the degree of control. If your controls are, if you have more of them, then it leans towards quasi-experimental. If you have diminished or no controls, it leans towards non-experimental. Our textbook made the differentiation between the two fairly complicated, but I think this diagram will give you some ease at identifying what is quasi-experimental and what is non-experimental. Quasi-experimental, you have an effort to make controls. If you don't have any effort to make controls or very little effort, it is non-experimental. So that is a big basis for a differentiation between quasi-experimental and non-experimental. Controls higher in quasi-experimental, no controls or minimal controls, then you are in the genre of non-experimental research. There is a process that, if you know it, you understand an awful lot about statistical analysis, and that is the process of hypothesis testing. If you understand the process of hypothesis testing, you're going to be able to look at any quantitative research article and dissect it into its parts and be able to make some statements about it regarding the quality of the research. Hypothesis testing starts out with a hypothesis. This hypothesis usually is stated in general terms at the start of an investigation. In order to do hypothesis testing, the hypothesis has to be testable. In order to make a hypothesis testable, you have to have independent variables and dependent variables that are concretized. Okay, concretized or concrete independent variables and dependent variables are variables for which you have an operational definition. For example, a general hypothesis might be that symptoms of depression will diminish after 5 sessions of cognitive behavioral therapy. That is not a testable hypothesis as it was just expressed. To make it testable, the independent variable, in this case, what we are trying to with our manipulation, that's going to be the CBT. That can be defined as CBT, 5 sessions of CBT with a qualified therapist. The dependent variable in the general hypothesis was simply stated as depression symptoms. We would have to make that concrete and use a measure of depression symptoms. Very often the Beck's Depression Inventory or the Hamilton's Depression Inventory or the System Checklist 90 are used. Now, Beck's Depression Inventory was not designed to measure the depth of depression. It was simply designed to be able to get a sense of whether depression was present or not. However, it is often used in this regard. So we might be able to make our hypothesis testable by saying scores on the Beck Depression Inventory will diminish after 5 sessions of CBT with a qualified therapist. Now we have operational definitions. They are concretized. Our independent variable is the manipulation, which is the CBT, and our dependent variable, it will be defined as the scores on the Beck Depression Inventory. Having done this, we have to decide what level of significance we're going to use. So the first thing is to make a testable hypothesis. The second thing is to choose a level of significance, which is commonly represented as simply P. The most commonly chosen level of significance is P less than 0.05. Now sometimes you'll see P written P equals 0.05. Either way is acceptable. This is the more hopeful form because what you're hoping is that the p-value of the statistic that you generate from your analysis will be less than 0.05. And you know that if P generated by our analysis, and we'll get into that in just a minute, is less than 0.05, if P is low, the null must go. However, if P is higher than 0.05, if P is high, the null must fly. So this is the hopeful way of writing it. It can be expressed both ways. You know that if you choose a level of significance of 0.05, your confidence level is going to be 95%. If this is expressed as a percent, as 5%, you just subtract that from 100%, that gives you your confidence level of 95. Now the p-value is the number of times with your data, normally distributed data, that you will be wrong by random chance. You are willing to accept 5 times out of 100 being wrong. Now, if you're working with a study guide, and 5 times out of 100, the study guide is not effective. 95 times out of 100, it is effective. That's not a big deal. However, supposing you were working with a medication and the side effect is death. Well, we only had 5 deaths out of 100. So what's the problem? Obviously, the significance of making a mistake comes into play when you are choosing a level of significance. If you are using pharmaceuticals that had a possible side effect of death, you might want to go with a significance level of 0.001, meaning that 99.9 times out of 100 you would be correct, and only 1 time out of 1/10 of a time out of 100 would you be incorrect simply by random chance. Okay, so you have to choose a level of significance, and you know that the most commonly chosen level of significance is 0.05. That is step 2. Now, step 3 is gather data. Which simply means you have to find your sample, randomly assign members of your sample to a treatment group according to the independent variable, which in this case is cognitive behavioral therapy, or to a control group. A very commonly used control group is a wait list. In other words, if you had a good number of subjects is between 20 and 30. But let's say you had 50 subjects for this experiment, and you could take half of them randomly assigned. You could number your 50 subjects and then have a random number generating software produce a random list of 25 to be assigned to your control group or wait list, and 25 to be assigned to your treatment group. The 25 in the wait list are going to be tested beforehand with a pre-test at the same time as the treatment group. And then you're going to apply your treatment and then test your treatment group and test the control group again. The passage of time may make some difference in depression symptoms as reflected in Beck Depression Inventory scores. That's why we need to have a pre and a post test with our control group. And you know that we are comparing one group with another, therefore this is a between subjects design. We gather our data. Now, having gathered our data, we are going to do a statistical analysis. I will post in our resource section a page from a statistics textbook that I'm using in another class that gives you the criterion for which statistical analysis to use. And mainly it has to do with the type of data that you have, whether you have continuous data, nominal data, and whether those are present in your independent variables and dependent variables, and then the number of groups that you have. Based upon the considerations of the type of data that you have and your number of groups involved, that will make a decision what statistical analysis you will use. Now, the statistical analysis is going to generate a test statistic. Test statistic. Statistic. And it's also going to generate a p-value of that test statistic. Let's just say the p-value generated by the statistical analysis that you have chosen is 0.01. And we had chosen a level of significance of 0.05. Looking at 0.01 and comparing it to 0.05, we see that 0.01 is lower than 0.05. If p is low, The null must go. Okay? Someone shared something interesting, kind of cute about Valentine's Day in one of our classes. Roses are red, violets are blue. If you were a null hypothesis, I'd fail to reject you. And in this case, we are going to reject the null hypothesis. So we're going to have a broken-hearted null hypothesis. But it seems appropriate. We just passed Valentine's Day. Okay, so your statistic analysis, whichever one you have chosen, is going to yield a test statistic and a p-value associated with it. You compare the p-value with the chosen p-value, and then you make a decision to accept or reject the null hypothesis. You know that this odd thing that we do in statistics about dealing with the null hypothesis stems from the fact that it's impossible to gather every possible situation in a hypothetical analysis. And so it's difficult to prove anything to 100% certainty. However, it is easy to disprove something. All you have to do is find one case that does not conform to the hypothesis to disprove it. So that is the reason why we deal with the null hypothesis in statistics. And that is the reason that I want you to include the null hypothesis in your critique of a journal article. And of course, the null hypothesis simply states that whatever you hypothesized, it doesn't work. In other words, in this case, we hypothesized, generally speaking, that depression symptoms would diminish after cognitive behavioral therapy. The null hypothesis would be that it makes no difference regarding depression symptoms if you use or do not use cognitive behavioral therapy. In other words, your treatment is not effective. That's the null hypothesis. So if you reject the null, you have accepted your treatment. So that in most cases, and in all cases, the researcher is looking to reject the null hypothesis. In other words, he's hoping that his statistical analysis will yield a test statistic that will, and with an associated p-value, that will be less than the chosen level of significance in the experiment. Okay, so this is the process of hypothesis testing. And if you understand the steps of this process, you can take any piece of quantitative research. You can dig into the hypothesis, see whether the general hypothesis is made into a testable hypothesis with concretized independent variables and dependent variables, with operational definitions. You will be able to make comments on this regarding the internal validity of the procedures used. You're going to see what level of significance they have chosen. You're going to see how they gathered their data according to their operational definition. You're going to see that whatever statistical analysis they used, it will yield a test statistic with a p-value. Now, it's very common that they will have lots of dependent variables. And so you're going to see in your research that such and such a measure was significant at the 0.072 level. If it was significant at the yielded a p-value of 0.072, if it did, it would not be significant because it's higher than the chosen 0.05 level of significance. So this is the process of hypothesis testing, and this is an extremely valuable process to understand because you can take it and apply it to any form of quantitative research. The part that causes people to cringe in fear of statistics is this area right here. That is not something to be afraid of, and I'm going to do a little bit of a demonstration regarding that in just a few minutes. Thankfully, we have the statistical package for the social sciences. We have lots and lots of online calculators that will produce the test statistic and the associated p-value for us. The difficult part for us is, number one, choosing which analysis to use, and I'm going to give you a chart which can walk you through that, and I'll post that in the resource section. And choosing it, and then understanding that you need to look at the resultant p-value and compare it with your level of significance. It's really quite simple. So try to get a handle on this process of hypothesis testing. Do not be afraid of this, because the most difficult part of statistical analysis is data entry. Okay? Having made a decision about what statistical analysis you'll use according to the criterion that I'm going to supply you, you're going to be able to simply plug in your data and then press calculate, and the software will yield a test statistic and an associated p-value upon which you can make a decision. Now, knowing this, you can also look at research and see for each of the dependent variables what their test statistic was, what analysis it was based on, and the associated p-value. The most important part being this right here, so that you can compare it with the chosen level of significance. So I've been a little redundant in my explanation here. I've explained it a couple of times. I hope that that's pretty clear. Please come by between classes and ask me questions if any of this is not understandable. I'd like to demonstrate just a little bit about what this 0.01 value, the p-value that is generated by the statistical analysis, actually means. You know that our statistical analysis depends upon the degree of normality in the distribution of the variables that we have gathered in our research. Now, a normal curve, of course, looks something like this, with most values clustered around the mean. Fortunately, most statistical analysis, if you have 30 data points in your set, can tolerate some degree of aberration in normality. Okay, most of them can tolerate that. To the extent that your data is distributed normally, to that extent your statistical analysis will be accurate. If your data turns out to be very skewed to one side or the other, then you're going to have some difficulties with statistical analysis. Fortunately, most analysis, as I just stated, can accept, can tolerate deviations from perfect normality. Okay? If you have 30 in your sample, you can pretty much assume normality. All right, I'd like to just make a hypothetical set of circumstances here and look at this distribution of data and label the mean as 100 and the standard deviation is 15. This is a good way to describe data, and if you are looking to understand something that you see in research, it's often good to make a little representation of a normal curve. Now, if I were to hypothesize that males in our class are taller than females in our class, and we'll do I'll do a demonstration of that for you later. If I were to hypothesize that males were taller, I would only be interested in this part of the curve. And if I were to say, I hypothesize that males in our class are taller than females, and that the difference would be statistically significant at the 0.05 level, I would put my entire level of significance on this side. Okay, this area here represents 5% of the data. This is P equal to 0.05. Okay, and this point beyond which 5% of the data are above it is known as the critical value. Now, supposing I do a test statistical analysis in the case of looking at heights in centimeters of males versus females in our class, and I find out that I get a test statistic that happens to be a test statistic of 126 and an associated p-value of 0.02. All right? Now, the p-value of 0.02 is going to fall at a point somewhere beyond the p-value of 0.05. It's going to fall somewhere in here, p equal 0.02, meaning that this area here, all the data here under the curve, is going to be 2% of the total distribution. Now, if these were the results of my statistical analysis, okay, I would know that the data point for p equals 0.02 is going to be right in here, 126. Okay, and it falls to the right of my critical value. And